So here we have the Excel spreadsheet, and we're going to work on the same problem then. Three reservoir problem where the three unknowns are the three flow rates. We know all the geometry of our pipelines, the length, the diameter, and the roughness, or well, the friction factor. Which, by the way, let me stop here for just a second and ask you before we go on to use the solver method. Right now, we're assuming that we know the friction factor. And so we use this iterative process. Let me jump back to the matrix here. We use this iterative process of solving the matrix, getting a new estimate of Q for each of the pipelines, letting that be the old, updating our coefficient matrix, solving again, and we just kind of go through that circular process. If we didn't know the friction factor, what would the process be? What does the friction factor change as part of this process?
As the velocity changes in the pipeline, it'll change the friction factor.
Okay, it does. It does. As we update the flow rate, it changes the friction factor. And how do we incorporate the friction factor into this analysis? When we look up there on the spreadsheet, where the friction factor is part of what? The C value, right? And the C value is part of the coefficient matrix, the A matrix. So if we had to find the correct friction factor, well, now that just means while we're updating our coefficient matrix, now we update C for each one of the pipes. Since we're updating the flow rates, there's nothing that says we can't update C. And so out here to the right-hand side, for every new flow rate that we did, I could actually have a column now that calculates the Reynolds number. I have E over D, and then I use like the Swami and Jain equation. And I update my friction factor. Then when I update my friction factor, I update my C value. And then I take that new C value down to this new matrix along with the new flow rates. And it all just falls into place. Okay. Now, if we had graduate students taking this class, that would be a requirement for them to do this with an updated C without knowing the friction factor. But it's really not anything that you guys can't do. You have that ability. You know how to do it now, right? It's just a few extra columns, and now we just update two things rather than updating one thing. Same process. Okay. And from there, you can now solve a pipe network problem where the friction factor is not known, but the type of pipe is known. And it just fits into the calculations. Okay. So how do we go about solving this now? I'm going to go ahead and add another sheet to Excel here. Laura?
For the friction factor, would we also take the average how we do for Q?
That would be the better choice, yeah. After we take the average Q, we use that to find the new friction value. Yeah, because otherwise it's going to oscillate, and actually the friction factor is going to help dampen it out. So if we were updating the friction factor, it might actually converge rather than being this oscillate one side and oscillate the other side, because the friction factor is a dampening function. But in the event that we're assuming a friction factor, or just to be on the safe side, even if we weren't assuming it, using the average flow rate is the better path moving forward than just saying, I'm going to take this new answer and apply it. Yeah. Okay. All right. So I'm going to call this the solver method. And if you remember back, for those who have taken civil tools, we talked about using the solver inside of Excel. The solver is very powerful. It's a very powerful numerical method or a numerical tool inside Excel. It does exactly the same thing what we've done here. You just don't see the engine running in the background, but it takes nonlinear equations and uses some form of a numerical method to linearize them. And there's more than one way of doing this, but it linearizes it, puts it into a matrix, and then just keeps solving it until it says, okay, I've reached some convergence value, and now I'm done. Here's your answer. Okay. So we're going to start off with the same thing using the solver method, but let's first talk about bringing the solver method up. A lot of times the solver is not turned on inside of Excel, And so you come up to File, and you go down to Options. Okay. And then over here on the left-hand side, you're going to see add-ins. So let me go through this again. Come over to File, Options, and then Add-ins. And down here in the bottom, then it says Manage Excel Add-ins. I'm going to go ahead and say Go. And this comes up here, and there's 4 add-ins that for whatever reason Excel doesn't turn on. And if you're doing analysis like in hydrology, it's good to have those analysis tool pack on. I've never used the Euro currency tools, no idea what those are. But the solver add-in I use on a fairly regular basis. So I would click solver add-in. So one more time here, you come up to File, Options, Add-ins, and then down the bottom, Manage Excel Add-ins. Now there's more than add-ins you can manage. You can add in comms add-ins, actions, XML, expansion packs, disabled items. You know, these are all the fancy things that Excel can bring in and increase its flexibility and capability. We're going to do the add-in, so go ahead and hit Go, click on Solver Add-in and OK. And you'll notice then that on the Data tab inside Excel, the Data tab, and I'm going to move this down here a little bit, but now this solver one was not there before. So we looked at it before I did that. It would not, the analysis would not have solver up there, but now it's there, and we can go ahead and use that. Okay. All right. So there's a lot of different ways of using the solver. But I want to show you what I think is the most robust. And the most robust is this simple concept. If I take all the equations that I want to solve and I set them equal to 0. So if there's anything on the right-hand side, I just bring it to the left-hand side and I set it to equal to 0. Then if I can force the sum of all the equations to 0 and at the same time force each equation to 0, then I've found a solution to my problem. And I say a solution because sometimes problems have more than one solution, okay? Especially if it's nonlinear. If it's linear, there's one. If it's nonlinear, there could be 2 or more, depending upon the order of the equations, all right? So it's really not that hard to do, and it has a lot of power and the ability to solve sets of equations. In fact, back in the early days when Excel first added this, and you know, I realize this has been 20 years ago, but I could solve, there's a particular design problem in open channel flow. It's converging channel because it creates what's called reflection waves. Well, it's 9 equations with 9 unknowns. Some are nonlinear, some are trig functions, and we had to program that up in Fortran. We also tried to use MathCAD to do it, and then Excel would just come out with this. I said, I'm going to try Excel and see what Excel will do. And Excel was actually more robust than MathCAD was at the time. Now, I don't know if they've improved MathCAD or not, but it could handle a bigger range of starting values. I could be more wrong on my guess inside of Excel, and it was robust enough to bring it back in where MathCAD would crash. And my programming was not very robust. That's the reality, is I didn't have any, it wasn't idiot-proof by any means. And so it was pretty impressive that a program that wasn't set up to be a math solver actually has some pretty good robust abilities. So I'm just going to go ahead and use function 1 as my first equation, function 2 and function 3 then as the additional equations. My first equation is already in that form. It's already in the everything equals 0 form, right? And I'm going to move this up here to match up those pipelines. Okay, so here's my first equation. Everything's already set equal to 0. Okay. Now I would note that Excel still has the same problem that if I put in a square value, it thinks, oh, you want me to square that. And it won't let it go negative, even though you'll see there's going to be a little box we can click inside the solver that says let the values go negative. It still has problems, so it's still best to put our equations in the form of using the absolute value. Okay. Now I don't have those. I thought I wrote those down here, but I didn't. Okay, so I'm going to redo these. Whoops. So my first equation is continuity. The second one's going to be my energy equation. And I'm going to then take the absolute value of Q1. Okay, and the same thing then for the absolute value of the old value for Q2. And then I'm going to bring my B vector, if you will, or my known values over to the left-hand side. So now this is going to be minus B plus A. So the sign is going to change on that, and all that then is equal to 0.
Why did you change the sign? Oh,
Because we brought it over to the left-hand side, yeah. So just doing a little bit of math there, bringing it on the left-hand side to set the whole equation equal to 0. Okay. Now I can do the same thing for the second equation. Once again, I'm going to insert the absolute values, and that should have been there. You know, I should have done this when I wrote these equations in, but so absolute value of the old value Q sub 1, the absolute value of the old value Q sub 3, and then once again bringing my reservoir elevations over the left-hand side. Therefore, the sign changes, and all this then is equal to 0. So there are my 3 equations with the 3 unknowns, Q1, Q2, and Q3. Okay. Any questions on this? Okay. So now I can come down, and I've still guessed if that Q sub 2 is going to be and let me kind of clean this up here a little bit. Okay. So now I'm actually going to write those equations. All right. So I have Q1 right here plus Q2 plus Q3 and all that. If it worked out correctly, if I had the right answer, that would go to 0. Okay. And then F sub 2, function, F stands for function or equation. So you could put either one there, I guess. So now this is going to be a negative C1, and remember we named those values. We gave them a name, C.1. So C1 times then the absolute value of Q1 times Q1 minus C sub 2, so C.2 times the absolute value, Q2 times Q2, minus then the HGL at B up there. Oh, not C2, sorry. I got to go back up here. HGL at B is 70 meters. There we go. I'm going to hit F4 to make that a fixed value, plus the HGL at A right there. And that there is my whole equation. So I hit enter once again. When that goes to 0, that means I will have a solution. And then my third equation clean up my spreadsheet a bit here. Okay, my third equation then is going to be the same thing, minus C sub 1 times the absolute value of Q sub 1 times Q sub 1 minus C sub 3 times the absolute value of Q sub 3 times Q sub 3 minus the HGL at C plus the HGL at A. Found a typo, that's not a good sign. Okay.
It was your absolute value references. You didn't close the parentheses on the second.
All right, there we go.
Dr. Savage, how come you only put the signs for the HGL value to stay the same? Like, do you not have to do F4 for all of them?
Right there where I just added that.
Yeah.
Yeah, I just missed it. Yeah, so thank you. And technically speaking, I wouldn't need F4 for these equations because I'm not going to copy these equations down. And so, but it's just good practice. I know that that number shouldn't change. And so, putting the absolute value, or not the absolute value, the absolute reference, got to be careful, difference between absolute reference and absolute value. And was that the question, the absolute reference, right?
Yes, thank you.
All right, yep, okay. All right, so now I have those three equations plugged in with those values. And what I want to do then is take the sum of those three. So, and once again, the note is if I can force the sum to 0, which doesn't necessarily mean that the individual equations are going to go 0, right? Because I could have a -1 and a 1, and that goes to 0. So I want to force the individual equations to go to 0 too. This is the technique that the solver uses. So I'm going to go ahead now and bring my solver up. So I'm going to go to my data tab and bring up my solver. It's going to bring up the solver dialog box, solver window here. It's going to say set the objective. Well, I want to force the sum of all those equations to a value of 0 by changing. Well, what do I want to change? I want to change my flow rates, which were my initial guesses. Okay. And I want to do that subject to the constraints. Oops. I want to add my constraints that I want the individual equations to be equal to 0. Okay. So let me go through that one more time here. All right. I'm going to bring my solver up, my data tab. Okay. And I want to force the sum of all my equations up here. I want to force that to a value by clicking on my radio button over here to a value of 0 by changing the variable cells. The variable cells are all my flow rates, my initial guesses. And then I want that to be I want to be subject to the constraint. So I'm going to add the constraint that all the individual equations themselves have to be equal to 0. Okay. Now, without getting too deep into the solver option here, I would note that down here at the bottom it says make unconstrained variables non-negative. The unconstrained variables are the ones we're trying to solve for. They're unconstrained. It means they can change. Okay, so I'm going to go ahead and click. That so it's not turned on because I want them to go negative if I have a negative flow rate. I want to have that ability. Otherwise, it'll say, okay, if it goes negative, then I'm finding the wrong solution. This is for when you know you're solving a quadratic and you only want the positive solution, okay? And that will force it to go to the positive solution. But in this case, our system, our set of equations, we want the ability for it to go negative. And I would note that there's solving methods down here, the GRG nonlinear, the simplex LP, the evolutionary. Without going into those, I'm just going to tell you, leave it on the default, which is the GRG nonlinear. Okay, oops. Make sure our variables are non-negative. We also have options over here where we can kind of set the convergence ratio, the convergence value. If you get into numerical methods, you'll learn about 4 derivatives, central derivatives, all this stuff. I'm just going to leave all that on, just the default values. You don't have to worry about messing around with it. When you got everything all set, you go ahead and hit solve. Could not find a feasible solution. Okay. So B25, 0, subject to these constraints. Okay, that should be all.
I noticed that you set your F1 equation to Q1 plus Q2 plus Q3 equals 0.
Thank you. Yeah, my equation, yeah, all right, that's exactly it right there. This is actually a pretty good mistake, actually. If you realize that you want to get this concept going, you want to figure out how to debug it. So, you know what I would do is I would come back here. If I already know, if I have a known solution, I'm setting this up and I want to kind of test my technique. So hopefully you have a known solution before then, right? So I could come back up here and we said these are the new values, right? So I could bring this back to the solver and I could stick those values back in here. And I would look at this and I'd say, look, these two are almost 0. This one is not, so that would be the starting point where I would look. And as Scott's pointed out, that is where I did make the mistake of not getting the right signs in there. So minus Q2, minus Q3. Okay. And since I started with those values now, those are essentially 0. But let's go back to just a good guess, 1, 1, and 1. You know, say we didn't know. And now I'm going to go ahead and hit the solver and go ahead and solve this. Notice. Let me cancel this. Okay, now I want you to focus down here in the lower left-hand corner. And you're going to see it move pretty fast. I hope it will catch it on the screen, but it will tell you the number of iterations that it's done. Okay, so watch down there, 1, 2, 3. And you see that that's the iterations it's going through. So it's doing the same thing that you did. All right, and I go ahead and click on OK. And, you know, if I clean these up now a little bit, you can see that these went to essentially 0. 10 to the 7th is -7th is 0. And if I come back over here and grab those values that I found using my circular method, bring it over here to my solver method, you can see that I have, once again, clean them up a little bit. I have the exact same answer. Okay. So in essence, you have, I'd say 1.5 methods of solving this by using Excel, because the circular method is just it's just a variation of the matrix method. And then you got the solver, and then you can do it by hand. Doing it by hand is something that is very important because it helps you understand the concepts. But you don't want to do by hand all the time. And so you could build a spreadsheet or write a program that would do this right here. Any questions on this? Feels comfortable with that? Okay. So this now will lead us into pipe networks.
For the homework, are we supposed to upload the Excel?
Yes. For the homework, I want you to upload the Excel sheet, the Excel workbook. Excel workbook. Upload your Excel workbook that has 3 tabs: matrix method, circular method, and solver method. Okay. All right. This will now allow us then to move into pipe networks. So let's talk a little bit about those. Pipe networks. Okay. So given a water distribution system, now it doesn't have to be a water distribution system. It could be, you could be working at a chemical plant But anytime we have loops, so a water distribution system with loops, and the question could be asked, well, why would we have loops in our network? And what is a loop? Well, a loop is where the pipe connects back to itself some way. It forms a complete circle or a complete shape that comes back on itself. And when we build city systems, we build them in loops. Why is that? Any ideas of why we would build them in loops? And this is the same reason why when we do fire protection, we talk about fire through our roads that we build for cities and communities. We don't like, fire departments generally do not like cul-de-sacs unless they're really short. Why is that? Anyone want to take a guess at that? What happens if you have a fire in a cul-de-sac and a tree comes down across the road? Let's say it's during a natural disaster, a tornado, and you get a tree that comes down the road, gas line breaks, and you've got a house that catches on fire in the middle, farther down the cul-de-sac. Makes it a little hard to get in there and help that fire, right? Or not even a fire. You get an accident happens out on the road, and someone down in the cul-de-sac is having a heart attack and they need an ambulance. A little bit of a problem, right? So we tend to want to have two entrances, or an egress and an ingress and an egress, kind of the technical words. So there's redundancy, and that's a key component of civil structure or civil systems, is we want redundancy. If something fails, it's not a problem, we're okay. We can follow it the other direction. And so a pipe network's the same way, that if we have a leak somewhere, well, we can turn off the valves within our system and still supply water to the rest of the system. Everyone's not cut off out of water. We may have a small group there that does not have it, but that's bigger than a large group that doesn't have it. So we will loop our water systems, plus we don't know when people are going to use water. We don't know when someone down the street's going to turn on every faucet they have, plus their outdoor system, because they're in doing laundry, someone's taking a bath, and they're washing the car and watering their garden at the same time. And it may be easier for the water system to supply water through two different routes to that house. But as soon as they turn that water off, maybe it only needs to come from one way, and the whole network balances itself out. But we have these loop networks. So the method of solving these, the method of solution is the same as the three reservoir. Primarily that the sum of all the flow rates equals 0, and the sum of the head loss equals 0. If we can meet those two constraints, then we have found the solution to our pipe network. All right. Now, for example, as an example, a basic diagram, basic network. Okay, I'm just going to draw this as some nice simple shapes. Okay, and we could have flow coming in. So let's go ahead and define this then as A node, B node, C node, D node, E node, and F node. Okay. And a node represents a location where there is a change that is going on. The change could be a physical change, such as it's a T or an elbow, but an elbow does not necessarily mean we have to have a node there. But if we're pulling water out at that node, then we're going to put, or if we need to make a change in the flow rate, we're going to put a node there. Now that would mean that in our system, every house would be a node, right? There would be a node, we'd have a straight line and node, straight line and node, which is a little bit overkill. Plus, not everyone uses the water at the same time, so we do something that's called skeletizing our system. In other words, we're going to group houses together, and we're going to say the house is on this end of the block. We're going to assume that they're pulling all their flow out of that node. You know, so we have houses right down here, and they are, I guess we kind of go like this, right? All the houses within that area are pulling the flow out. So we're going to group the flow at that node. Okay, so I could have flow coming in, Q sub A supplying my network. When I get to Q sub B, now I may have flow going out. And Q sub C could have flow going out. And Q sub D has flow going out. I'm going to say that there's no flow going out on Q sub B, but it's a T. So the flow splits. All right. And let's put flow out on Q sub D here as well. Okay. And we're going to define then a loop is where the flow goes around. So in this particular scenario, I have one loop, I have two loops. Now think about when we did branch pipe networks. We said it doesn't matter if you take if you took B, so we have pipe A coming in, it splits into B and C, and joins back up into D. We said it didn't matter if you took B or if you took C, you ended up at the same spot. Okay? So my concept here is if you start at A and you walk around loop one, so you go from A to B, E, D, and back to A, and you're thinking about the hydraulic grade line. And at A, let's say you have a hydraulic grade line of 100. When you walk all the way around the block, the hydraulic grade line when you come back to A has to be equal to 100, right? Imagine the hydraulic grade line like an elevation. You can go up, you can go down, but when you come back to the same spot, it better be the same. So that's the concept right here, that the sum of the head losses around a loop, sum of the head losses around a loop equals 0. And the sum of the flow rates at a junction equals 0. In other words, what comes into the junction better be what's going out of the junction. So if I can balance the flow rates at all the junctions and meet the continuity equation, and if I can balance the sum of the head losses around a loop and meet the energy equation, I've solved my problem. Okay. So that's the concept of pipe networks. It's nothing any different than what we've been working on with 3 reservoir problems. It's just going to get a little more evolved because now we're going to have more pipes. And we're still going to start adding components to this. Okay. So additionally, we can say then, we need to define some terms. We can say P, this equation P is equal to J plus L plus F minus 1, where P is equal to the number of pipes, L is equal to the number of loops, J is equal to the number of junctions, okay, and F is the number of what we call fixed grade nodes, or fixed grade fixed grade nodes. So fixed grade node. So I think the number of pipes is pretty explanatory. The number of junctions is pretty explanatory. The number of loops is pretty explanatory. Now we need to talk about these fixed grade nodes. Let's assume that we had reservoirs on our system. Okay. So if we brought in and put the flow rate coming into our system was coming from a reservoir, now we have a reservoir would be considered a fixed grade. And the grade is representative of the hydraulic grade line. That's where the term grade comes from, hydraulic grade line, fixed grade. It means we have something that has a fixed that showed up there, right? Yeah, fixed grade, okay. We have something that has a fixed head to it. It doesn't matter how much flow we use, the head is going to stay the same. So if we have a big tank, it doesn't matter if we're using 2 cubic feet per second or if we're using 1 cubic foot per second, the pressure at that node is going to stay the same. Now remember, this is a snapshot in time. Everything that we're doing right now is steady state analysis. Unsteady state or transient analysis, those are down the road. I don't know that we'll necessarily get to those in this class. We'll talk about them a little bit when we get to the software that we're going to use. But we need to make sure that we can solve steady state, this one snapshot in time. If I define my nodes, I define all my geometry, what's going on in my system. We have to do that first, and then we can start stepping through time and see how things change. So F would be the number of fixed grade nodes, okay? So this kind of gives us an idea of what we need to solve our system. Now, if I would have went back to this system, and I probably should have done this before I added that fixed grade node coming in, but let's just do this really fast. So if I do example number 2 here and just do a really quick sketch of the same system. Okay, flow coming in, I'm going to have a few flows going out. I put those at various locations, it does not matter. A, B, C, D, E, and F. Okay, if we were to look at this, we'd say, well, there's 7 pipes here, right? So P is equal to 7. Number of loops, so loops is equal to 2. J, the number of junctions, is equal to 6, and the fixed grade nodes is equal to 0. All right, well, does this hold true? Well, sure, 7 is equal to 6 plus 2 minus 1. That holds true. Good, makes sense. Our system is solvable. However, in this particular case, we would say, what are our equations available to us? Well, I have 7 unknowns, right? So my 7 unknowns are Q1 all the way to Q7. The flow rate in every pipe. And we can even number those pipes. Go 1, 2, 3, 4, 5, 6, 7. 7 pipes. So I have 7 unknowns, so that should tell you how many equations do you need? 7, yeah. 7 equations. Well, what are those equations? Okay. Well, I know I have a loop here, and I have a loop here. So the equations that are available to me are as follows. So available equations. What do I have at each one of those junctions? Flow in and flow out. Flow in and flow out. So I have continuity at every single one of those junctions. So I have 6 continuity equations. Okay. And I have 2 loop equations. So it gives me a total of 8 equations. You say, well, I only need 7. So should I throw out one of the energy equations? The answer to that is no. You want to keep the energy equations. But if we were to do a rigorous analysis of this, you would see if we wrote down all 6 continuity equations, we could prove that one of those continuity equations is redundant, meaning that it's just the same thing as one of the other ones, but in a different form. Or another way of looking at this is that if we use 5 continuity equations, we've automatically identified what the sixth unknown is because it's built into those 5, right? If I have a node where 10 cubic feet per second is coming in and 8 is going out in one direction, well, I automatically know the flow in the other direction, right? And the other pipe has to be 2. So that's redundant, if you will. I don't need 2 equations to describe that. One does it. So one of the continuity equations is redundant, and it doesn't matter which one you throw out. It's redundant. So you can pick 5 of the 6, and it'll be just fine because they all work together. And the 6th one is redundant, whichever one you say is number 6. Okay? So to solve this problem right here, I would select 5 continuity equations. Unfortunately, those continuity equations are linear. 5 linear continuity equations. I would pick 2 nonlinear equations, which are my energy equations. My energy loop equations are nonlinear. Okay? So let's take a look at what the, let's go ahead and write these equations down. Okay. Now I'm going to add one more notation to this. I'm going to say the flow going out is a demand. So demand out. So this is D sub C, and this would be D sub F, and this would be D sub E. Now the flow at A is a supply. That's what's supplying my whole network. All right. And I'm just know that that's coming in. So I'm going to define now my sign convention. And this is my personal sign convention. Once again, you can flip it. You just got to stay consistent. For me, the sign convention is going to stay with what we've already done. At the nodes, in is a positive, out is a negative. For a loop, I'm going to say with the flow is a negative, and against is a positive. With the flow, I'm going down the hydraulic grade line. I'm losing energy because friction's taking it out. If I happen to be walking up the other direction, then I'm going to be adding energy back into my system because I'm going against the flow. Okay? So I can define then by coming up and making some random guesses. I really wish color would show up a little better on this, but I'm going to take some random guesses. The flow is going to come in, and I'm going to assume that it goes down 1. So the next step is down here. We could say, assume flow directions. Now, I may or may not know the direction that the flow goes. If I do know, then go ahead and put it in there, but otherwise, just take a good guess. So I'm going to assume that since it's coming in at A, it's going to go down 1, and it's also going to go down 3. I'm going to assume that it's going to go across 6. I don't know what it's going to do on 4, so I'll just assume that it's going to go down on 4. Go across on 2, and go across on 7. And I don't know, I'll put it down on 5 as well. So I've assumed those directions for my flows. Arbitrary directions. The only thing I really know is that it comes into A and it has to go either down, it has to go across 1 or down 3. It doesn't necessarily have to be both of those, but it has to be at least 1. I mean, it could do the, well, actually, I don't think it can, it can't really come back to A, actually. Both of these have to be in that direction, but that's okay, it doesn't matter, okay? So now once I've assumed those flow directions, I can now write my continuity equations, okay? And then I can write my energy equation. Now we're out of time for today. That's what we're going to pick up on Wednesday. I've posted a little handout on Moodle, so you have the homework that is due Wednesday on the 3 reservoir problems. I would also recommend that you read the little handout. It's a 2-page handout. Kind of goes through in a little more detail of what we've done today. And then on Wednesday, we'll start writing equations and solving pipe networks. Okay? So have a great day. See you on Wednesday.